I will begin with a word of prayer. Heavenly Father, we thank you for this day. We thank you again for your creation. Just help us to understand it a little bit better today, Lord. In your name I pray, Lord Jesus. Amen. All right, so we have reached lecture 18. And today I will hopefully explain to you a little bit about what is the vector potential. As I think back fondly on this course, this is one of those things that distinguishes this course from the other course, you know. But before I do that, I should talk to you just a wee bit about magnetostatics versus electrostatics, right? So essentially, we have these equations, right? The divergence of the electric field is rho over epsilon naught. The curl of the electric field is 0. The divergence of the magnetic field is 0. And the curl of the magnetic field is mu naught times J, right? So these right here form the theoretical core, if you will, of electrostatics and magnetostatics. Now, of course, there are terms and conditions, right? What are the terms and conditions? Like the charge density, it has to be what? Can it be changing in time? No, that would not be electrostatics, right? So the charge density is constant. It's a static charge density that we're talking about. We didn't even think about that much, but that was always the assumption of the previous story arc in here, right? Chapters 1, well, 1 was just fun, but 2 and 3, right? And then now we're assuming that J is a steady current, right? Which means that the charge is not piling up anywhere, right? So I suppose what that means is the continuity equation I talked to you guys about last class is not properly part of either of these stories, is it? Because if we're talking about the divergence of J is equal to minus, partial rho partial t, well, that's from another world of discussion, right? But these 4 equations taken collectively are what are known as what? These are Maxwell's equations. Of course, at the moment, we're in a very particular case of that, but there it is. Now, you guys know the deal. Now, he also says, he says, Griffith is like, and they're also paired with boundary conditions, right? Like usually we assume that the electric field has to go to 0 as we go far on out, right? Or the magnetic field has to go to 0 if we go on far on out, right? Oh, except when we're dealing with every toy model that we talk about most of the time, right? Like the infinite line charge or the infinite plane charge or the infinite current. Pretty much all of our examples violate this electric field and magnetic field go to 0 principle, right? Because those examples with the maximal symmetry are maximally fun to work with. But of course, if we actually did have a finite distribution of charge and a finite current distribution, then yes, the electric field and the magnetic field should be going to 0 as we get far out, right? So that's true. And okay, so in terms of the theory of potentials then, this right here, what did this tell us? We could put E equal to minus the gradient of the potential, right? That was a reasonable thing to do because we could in fact define V of R to be equal to minus the integral from wherever our 0 was set for the potential of E dot dl, right? And why was that? Why is this a reasonable, meaningful definition of the potential? Why is that?
I mean, the reference point doesn't change the electric field.
Right, but like, why can't I just say this line integral is done from the reference point to the field point? It's a conservative field, right? The electric field is conservative because of this. right? Now, of course, what was the other way we could calculate the potential? Remember, the other thing we did was, what was it, 1 over 4 pi epsilon naught. We do the integral of, how's it go? Rho of z r prime d tau over the script r, right? Or if you like, I'll be explicit here for a second, r minus r prime, right? There you go. We had those two options, right? If you have the electric field, you could calculate the potential, doing the line integral. Or if you have the charge density, you can do this integral, you know, basically calculating the potential energy per unit charge for the total distribution. The sum of all that forms the potential due to that distribution at the field point r. This is just a review. You guys know this stuff already. You all said these things on the test, right? I think so. Now, this here, the curl of B is mu naught times J. What does that mean? Like, okay, so suppose theoretically for a second, you know, assume for a moment that B was equal to minus the gradient of, I need another letter, let's say psi, for just a second. Suppose that was the case. Why does this get us into trouble? Well, if this is my current, right? Let me use I for current, all right? And if I had this, if I could find a scalar potential for the magnetic field, and if I have a current somewhere, right? If I take a loop around that current, right? I can then calculate what, like, you know, the integral of B dot dl, right? Let me call this thing S, right? Around the boundary of S is equal to what? Well, it's equal to the integral over S of the curl of B dot dA, right? Which is mu naught times the integral of J dot dA, right? Which of course you guys know the story. This is mu naught times I enclosed, which in this case I'm saying is I. All right? Well, if there was a potential, this would also be equal to the integral of minus the gradient of the potential dot dl, right? And so if I take this point as point 1 and it's also point 2, I can look at the boundary of S as the integral along the curve that goes from, you know, S1 to S2, all right? And then this would be like minus psi of, you know, 0.2 plus psi of 0.1, however you want to order them, whatever. But the point is, those are the same point, and this would be 0, right? But it's not 0. But it's not 0. So what gives? It's not conservative. Not, at least if we go, I mean, okay, so here's the thing, guys. Conservative, not conservative, only is meaningful with respect to a domain. So if I was to, you know, not encircle, if I was to look at a domain which didn't encircle the current, all right, then I might be able to still find a potential for it. Like, we could try. Let's be explicit, yeah? So you guys, we'll do, let's try to work this out here, if we can. I mean, this may not work, I don't know, I'm just trying this right now with you guys. So z-axis, we'll put the current like there, right? We already know the formulas for that current, right? What's our formula? Magnetic field, mu naught I over 2 pi s, right? Times what? Phi hat, right. So let's just take it for a spin. Let's see. I mean, I know this is the calculation we just did over there, casting a very long shadow on the successor, the potential success of what we're trying to do here. But let's nevertheless try to do it. U naught I over 2 pi s, and this goes in the, phi hat direction, right? And the question is, can we find minus gradient of psi to solve for that? Now, we know full well that's not going to work if we go all the way around, okay? So something's got to give. Hopefully we'll see that. Now the question is, what is the gradient in, what coordinates should we use here? Cylindrical coordinates. What's the gradient in cylindricals, remember? You got yourself a minus s hat, partial psi, partial s, plus, listen to me, minus z hat. I'm doing the part, I'm just doing the part that's easy. You guys tell me the last part. Yeah, I want to say it's phi hat over s. I could be wrong. You guys have the book? You're checking? Okay. All right, so if we try to do this, what we need is mu naught I over 2 pi s, right, equal to like minus 1 over s. So were we right about the 1 over s? Was I right? I mean, I'm pretty sure I'm right. For dimensional reasons? Do you guys understand that? For dimensional reasons? Because we're like basically dividing by dimension.
Correct.
This is an angle, so we have to put an s there to make it, yeah, this is correct, okay, good. So can you guys solve that? What should we make the, so apparently psi is what? I mean, maybe we should definitely not have psi as psi is definitely not a function of what? Psi equals to psi of what? Of phi, right? We'll set partial psi, partial z, and partial psi, partial phi. Oh, wait a minute. Other way around. Partial s, right? We set those equal to 0 so that we don't have to worry about these guys, right? Then we try to match up the phi hat part, right? These s's, they be canceling. And so we have minus mu naught I over 2 pi equals to, it's actually the total derivative, isn't it? Because it only depends on phi. So integrate, and we get that psi of phi actually is simply minus mu naught I phi over 2 pi. But I thought I just proved this couldn't be done. So how did I do it? Like, okay. So let's try this. I take a loop, right? That starts here, maybe, whatever. It's encircling like that, all right? So let's say it starts at, phi 1, and it goes over here to phi 2. Start. End. And I want to calculate, what's the integral of b dot dl along this curve. So I do, okay, so it's, minus the integral of the gradient of psi dot dl along the curve, right? Which ends up being mu naught I phi divided by 2 pi, right? Evaluated from phi 1 to phi 2 if I haven't messed up my signs and stuff. The minus and the minus, they cancel. And so what do we get? We get mu naught I over 2 pi times phi 2 minus phi 1, right? So if we take the limit as those points approach, we get mu naught I times 2 pi over 2 pi, yeah. So what's the problem then? How is it that this is working, but this is the contradiction? What gives? This is the issue you have to face and understand if you really want to understand vector calculus. You must understand this. Until you understand what's going on, you don't really understand vector calculus. But this is the subtle thing, you know? The issue is that, and it's a very subtle thing, actually. So maybe I'm being a little bit too dramatic, but this cannot be continuous. All the way around. It cannot be, because it has to have the 2 pi jump. But remember, if it's differentiable, it's necessarily continuous. So we can only locally satisfy that the magnetic field is the gradient of a scalar. But if we encircle a wire, it's going to break down. So that's why Griffith says that you can only find a magnetic scalar potential if you're very careful to only suppose that you have a potential with respect to simply connected regions which don't, have wires. Like anywhere there's a wire, that's punching a hole through your region, because where the wire is, the magnetic field's not defined, and where the magnetic field's not defined, the scalar potential is not defined, right? And so, like, if I have some region, some blob, right, and it has a wire going through it, like this, all right? That means at all these points, going from one side of the blob to the other, those points are deleted from the domain of your scalar potential. They have to be, because the magnetic field blows up at where the wire goes, right? That's the very nature of, where did I write this stupid thing? Here, this thing, right? Look at that. When S goes to 0, B goes to infinity, right? And if that's the case, right, if you have a current going through your volume that you think you've found a scalar potential for, you haven't. Because if you encircle that current that's producing the magnetic field you're trying to find the potential for, you have to get the integral around the loop is 0. And yet it can't be 0 because you have the current. But in terms of the topology there, the reason is that this blob with a thing deleted like that from one side to another is not simply connected. If you take a loop that encircles the deletion, right? There's no way that you can smoothly deform that loop to a point over here. You get stuck right there on the deleted part. So you can't collapse the loop to a point. It's not simply connected. So the issue of finding or not finding a scalar potential for a magnetic field is inherently a topological question. And I don't think we fully understand the import of topology into physics yet. I think we're still at the edge of that, guys. Anyway. So something has to give. This is obviously undesirable, right? You don't want to have to, chop your space up into these little, wedges that don't have holes in them, and you have to find a different scalar potential for each little piece, and work weaving those together like some sort of patchwork quilt. Like, you could do that, right, if you wanted to, but you don't want to, right? Because I've only thought about the issue of line currents, but I'm not sure what happens to this discussion when we think about like, well, I guess I kind of know what happens when we have a volume current, right? Something similar. But what about like a surface current? I don't know. You can think about it. So enter, given B, a magnetic field, we say A is a vector potential if D is given by the curl of A. Now that's wild, right? When I first saw this, I'm like, what? What is happening in this course? Why? Why would you, how could that be helpful? You're saying one vector field is the curl of another vector field? That seems horrible, right? You have this dim memory of taking curls in Calculus 3. You remember something you learned how to do, and it felt like a welcome relief from, checking Stokes' theorem or something, but still, it's tricky. It's all of the joy of a cross product, but also differentiating, So how on earth is this helpful? Well, it nevertheless, so the thing I haven't emphasized yet today, and I really should, is the other Maxwell equation for the magnetic field, del dot B equals to 0, right? What is that called? No magnetic monopoles, right? So, if we put B equal to del cross A, notice for one thing, if we look at the divergence of B, that becomes the divergence of the curl of A, and there is an identity of vector calculus which says that the divergence of a curl is automatically 0. So we got that. Woohoo! All right. So first of all, if we have a vector, if we could find a vector potential, if such a thing exists, right, then certainly it automatically satisfies the no monopoles. There are no magnetic monopoles. Now there's a discussion in Griffiths I should talk about, and I guess I'll talk about it now. It's kind of a digression from my current thought process, but let's just get it over with. He says that, and you maybe remember, do you remember from your previous course the statement, magnetic field lines have to come in loops? You remember that? There's just one problem with it. It's false. Yeah. Now, natural question, oh, it's false. Well then, sir, give me a counterexample. That's the reason this lecture is not better prepared, because I spent about 3 hours yesterday trying to come up with a counterexample. I do not have one. I have a conjecture about a counterexample. I think that if you look at I think if you look at a current that starts here, like this, so R of t is like RT, oh, good grief, R cos t, R sine t, HT, and I'm talking about a current that follows. So what I'm saying is the current follows the helix. A helical, and it goes, I'm just drawing the positive half, but let's suppose it goes on and on forever and ever, amen, all right? So it's infinite helix current. You don't have to ask the question of where it starts because it never started, right? See, that's how they do it over there in the non-creationist side of things. You don't have to explain the beginning. There was no beginning. Problem solved, right? Oh, what am I saying? It's just a multiverse, right? So anything special, you just explain away, because there's a landscape. There's a multitude of universes, right? That's not an explanation. But anyway, it's very popular these days. Anyway, I think that if you studied this particular current distribution, what you'd find is that the magnetic field line does something like this. Oopsie, I lost track of where I was. Anyway, you get the idea. Now, that's not a closed loop. So to be more careful, I think, what we should say is the magnetic field lines never stop, and they never start. They must go on forever. Sometimes they go on forever in a closed loop. In all of your favorite examples from Physics 232, they in fact do form closed loops. The solenoid, the toroidal solenoid, the current loop, all of these actually have magnetic field lines that are loops. All right? But there was actually a paper published in like the 70s or 50s, sometime in the last 20th century. Like, there's a footnote in Griffiths for the paper. But if you go looking, I have not found a nice, simple, concrete example. The calculation of the Biot-Savart equations from this are formidable. I found them. They involve some sort of Bessel function integration. I'll send you guys the link if you're interested. But so that's the thing, is like the calculation of the magnetic field is quite insidious. And after all that's done, I still need to find the integral curves to the magnetic field to find the field lines. See, the field lines themselves are integral curves. They're curves that the tangent vector field to the curve lines up with the vector field. That's what it means to have a field line, right? Is that the tangent vector field to the curve is the vector field which we're finding the field line for. So anyway, there's like a page in Griffiths where he essentially comes to the viewpoint that he's not really sure that magnetic field lines even make sense, because you can't count the ones coming in and out or something. I don't really know what that paragraph means. I don't actually think counting field lines is a heuristic for a mathematics, which is the flux integral. The flux integral makes sense for magnetic fields. There's nothing to worry about, all right? It's just not true that they're always closed loops, is all that there is to say. But that doesn't make the concept of flux any less meaningful. All right, so anyway, it is still true though, because the divergence of the magnetic field is zero. If you take a closed volume, right, whatever the total number of lines, flux, field lines that are coming in one side have to be going out the other, because the net flux through any closed volume must be zero for a magnetic field, right? But they don't have to be closed loops. They could be that. All right. I think, and this is a conjecture. I haven't proved that. For all I know, this still has closed loops. They're just, I don't know.
The limit is just a line charge.
That's the thing, is if you take the appropriate limit, and squish this down, and also let it still be very long, well, there's a couple different limits to think about. One should be a current loop. Another would be the densely wound solenoid. So whatever the mathematics is here, it should produce a couple of different examples and different limits. Or if you just stretch it out straight, it should be the infinite line current. Yeah, that's true. Yeah. Now that I have got this entirely unproductive conversation out of the way, we've had this talk, so now you know, if somebody comes up to you and goes, "What do you think? Are magnetic field lines always in loops?" You can be like, "No. It says so in Griffiths. Proof by Griffiths. Haha." All right, there you go. So, next question, guys. What happens with Ampere's law? Right? Reminder, Gauss's law, right? What did we do? Took the divergence of this thing, right? Well, not the divergence. We replaced the electric field with minus the gradient of the potential, right? And that gave us, what was this called? Laplacian of the potential is minus rho over epsilon naught. Remember this? This was Poisson's equation, right? We spent a whole chapter solving this thing, right? Remember? Okay, great. So all kinds of bells and whistles are available for solving that equation, as we've talked about in some depth. All right. How about the vector potential then? So we have the curl of the magnetic field is equal to mu naught times J. All right, so that says that the curl of the curl, yowzers, the curl of the curl is equal to mu naught times J. But how did the curl of the curl work out? Do you guys remember?
I have the gradient of divergence of A minus Laplacian of A.
The gradient of the divergence of A minus the Laplacian of A is equal to mu naught times J, right? So that's what we're up against now. Now, at first glance, that looks kind of like, that doesn't give us much hope, does it? But something amazing happens here. Is we can impose the Coulomb gauge condition. And the Coulomb gauge condition is simply the assumption that the divergence of the vector potential is 0. If we impose that condition, then what that gives us is simply that the Laplacian of A is equal to minus mu naught times J. And so what that means, right? What does that mean? So that's actually what? Like the Laplacian of the x component, right, is minus mu naught times the x component. The Laplacian of the y component is minus mu naught times the y component of the current density. The Laplacian of the z component is minus mu naught times the z component. So we actually have not one, not two, but 3 Poisson equations. Which means you can solve this in the same way that we solved the Poisson equation before. We can solve this equation if we're working with the Coulomb gauge. Now, if the Coulomb gauge is not fixed, if we don't have the divergence of A is 0, well then other things are required. All right? But given that the setup is the same, what's the formula for A? Like, I wrote down the formula for V earlier, right? It was what? The integral, this here, right? Let me write it down again, over here. What was the solution? What was the solution to Poisson's equation? I'll write it here. It was what? We wrote V of R was the integral of 1 over 4 pi epsilon naught, right? The integral of rho of r prime d tau prime divided by the script r, right? That was our solution to the Poisson equation. We just have to integrate the charge density times the reciprocal of the display, the separation distance between source and field point, right? Did I do something?
Is it d tau prime?
Yeah, technically speaking. Did I not put the prime over there? Yeah. In my heart, there's no prime. But there you go. So, by complete and total thievery from our previous discussion, what's the formula for the magnetic potential then, in terms of the current density? A of R is equal to what? Compare. So we don't divide by epsilon naught, we multiply by mu naught, right? So we got mu naught over 4 pi, you say? the integral of, what is it? J of r prime times d tau prime divided by script r. There you go. But notice now that we're integrating a vector. I don't have an example yet for you guys where I actually work directly from this formula to find A. Maybe next time. But there's already something you can see from this. What is this like? Just look at this integral. What does it say about the direction of A? What should you expect? Which way does A point? Right, it should be pointing in the J direction. So we should kind of expect our, our vector potential to point in the direction of the current source for the distribution. Now, there's a curl involved, so doesn't have to be. Like, let's talk more about that. Let's talk more about that. So, what I'm talking about right now is largely known as gauge freedom. So if I have V1 and then I have V2 is equal to V1 plus a constant, or if I have, A1, or if I have A2, which is equal to A1, plus, check this out, the gradient of an arbitrary function. Right? So if the electric field is minus the gradient of V1, well, guess what? It's also equal to minus the gradient of V2, since the gradient of V1 plus C is just equal to the gradient of V1, right? And how about if the curl of A1 is B, the curl of A2, guess what? It's safe here. No one's going to say chicken butt. Okay, it's good. Phew. Man, if I said that at home, I'd have walked right into it. But anyway, so magnetic field, if it's equal to the curl of A1, well, that's equal to the curl of A2. Since the curl of A1 plus the gradient of F is the curl of A1 plus the curl of the gradient. But what is the curl of a gradient? It is 0, right? So this shows you the curl of A1 is equal to the curl of A2. What this means, you guys are well familiar with the fact that the potential is not unique. We can make the 0 for the potential wherever we like, right? Unless some evil professor has made it be 0 on an infinite ground plane and you're stuck with that, right? But short of those kinds of lack of freedom, right? Professor-dependent lacks of freedom. Setting those aside, you have the freedom to make the potential 0 wherever you like, as long as you're not trying to make it 0 across something that's not an equipotential, right? Like if your problem has a change in potential across this line and you try to make the whole line be equal to 0, well, that's not allowed either, is it? So but you can, if you have an equipotential surface or line or region, you can make that equipotential region 0. You have this freedom. That's gauge freedom for the scalar potential. The gauge freedom for the vector potential is far more vast, because this F is an arbitrary function of 3 variables. And for that reason, we're able to impose the Coulomb gauge. Maybe I'll explain the details next class, all right? I just want to work I want to work a couple more examples this class instead of getting into the mathematics of that, yeah? So, all right, let's work a concrete example. Suppose we have, I guess this was example what? one. I don't have this in my notes either. I need to write this out. This needs to go in my notes. Example 2, I'm messing up my notes numbering now. Oh well. And I gotta wait up and I'll fix it. So suppose our magnetic field is a B naught, let us say Z hat. All right, I would like to find a vector potential for this constant magnetic field. Now, I have not already done the homework problem I've assigned to you guys, which gives you a like stone cold way to find the vector potential for an arbitrary constant magnetic field. That's one of your homework problems. Super cool. So before that, we have to use other means, which is our current means are simply to try to solve it. So like the curl of A, what is it? Well, partial AY, partial Z, minus partial AZ, partial Y, comma, partial AZ, partial X. Wait a minute, hold on a second. I think that's XZ. Yeah, minus partial AZ, partial. I mean, you guys could cheat and look in the, you know, what you call it, the cover, whatever. Partial Y, partial X, and finally minus partial AX, partial Y. All right, there you go. That's the curl. And we want this to be equal to what? 0, 0, B0.
Is the first term negative?
What?
Yeah.
Oh, rats. Yeah. I should look at my notes. I bet it's right in my notes. I know that they're differ by a sign, right? I mean, that much is inescapable. All right. So now is the time we make choices. Choices born of convenience. Choices that could go another way, but the choice I'm going to make now is I'm going to make AZ and AX equal to 0. You know why? Because I can. And if I do that, make AZ and AX equal to 0, what am I left with? I'm left with partial AY, partial Z has to be 0 from this one. The middle term is gone because I made those 0. All right. Choice. And then I have over here, because I made X here, I got partial AY, partial X equal to B naught. So this, I would suggest that A sub Y is equal to B naught X. And if I do that, this is automatically solved. Therefore, I can use A equal to 0, B naught X, 0, if you like. And you can check that the curl of that A is that constant magnetic field. Now, I made a lot of choices here, didn't I? But do we have to find the arbitrary form of the vector potential? Not necessarily, right? If the question is just to find a vector potential, we've done that. Is this the only one? Oh no, certainly not. I can tack on, you know, plus the gradient of f for an arbitrary function. Any function you like, add partial f partial x here, plus partial f partial y there, plus partial f partial z there, it still works. there's a plethora of possible vector potentials for this constant magnetic field. But that one works. Let's see if we can understand this in terms of, okay guys, so you guys help me out. Where would this kind of infinite magnetic field come from? Let's suppose that this is just for Z positive. All right.
Cylinder.
Oh, I don't want just Z positive. I'm sorry. I want, my bad. I want X positive. So like, so the magnetic field's like this, right? I'm an idiot. The magnetic field's like what? Like this, right? So, and that's not helpful. It's just in the way of my picture. I'm put over here. I think we can consider an infinite plane current over here. And I want to say probably, I bet it has to be in the y direction. I bet we need a plane current like this, like an infinite sheet current here. If I did that, no, that doesn't do it. I haven't thought about this part yet. I was trying to do this on the fly.
Would it be X, Y plane so you can have a point in the Y?
Well, I guess the example, this one, right? If we had this is our infinite sheet current. If we think about this, the magnetic field goes up here like this, right? And then below it goes like that, by like the Ampere's law with a little loop here. So like if the current's coming out at me, the magnetic field's going that way. So I'm trying to think of what current, what planar current will give me an upwards magnetic field.
Yeah, it just increases in X instead of Z. Yeah, the current is going
Oh, I need to go. Thank you guys. So like this. Then, yeah, then I can't do it, but that way. All right. So that current is what would give me that constant magnetic field. I'm just trying to see if I could see like this current and that in terms of the formula over there. I don't know if it really worked or not, you know? Like I said, it doesn't have to be exactly that, but it might be. I'm not sure there was any insight gained. My J is in the, allegedly my J is, you know, which way? Like K is, K hat is X hat, right? So, yeah, it's not, it doesn't just directly, okay, fine. I was hoping it would work directly, but I did make many choices here, so. Okay, so last example for today. Can we find the vector potential for my example one? Let us not be content to leave, like, let's find the vector potential for the most important example, right? The infinite line current. So what do we have to do that? Oh, definitely not. Heavens no. There is an easier way. Instead, it's not wrong. I mean, that's a completely reasonable take on what I've written on the board. It's just what I want to do is just this a straight analog of my example 2, but in cylindrical coordinates. What's the curl? See, this has to be the curl of A. And what is that in cylindrical coordinates? Well, in cylindrical coordinates, the curl of A, I had to look it up. but it's stuff. Fine, I'll write it out. 1 over s partial az partial phi minus partial a phi partial z s hat plus partial as partial z minus partial az partial s phi hat plus 1 over s, big parenthesis here, partial s of s times a phi, close parenthesis here, minus partial as partial phi, and that is in the z hat direction. And with that, it's not bad. We can do this. So look, we need, this needs to be 0. We need this to be 0. Oh, excuse me. Nope, this is not 0. This is what? This is mu naught I over 2 pi s, right? We need that. And we need this guy over here to be 0 again. Now, there are infinitely many ways to solve this, but I propose that we make a sub s and a sub phi equal to, how about 0? Because if I do that, much like the previous example, this bunch of partial derivatives I have to satisfy boils down to just a few, which I can manage. And this, by the way, is my usual technique for solving curl problems. I try to make stuff 0 and see if that will allow me. Okay, so like this one becomes what? The z remains, right? So I've got like partial a, z partial phi has to be 0 apparently, right? From that, this one, I'm saying the s is, so that must be that minus partial az partial s, that has to apparently be mu naught I over 2 pi s. That's interesting. This one over here is 0. All right, we're good. Look, so actually, just like my previous example, this one here, we can integrate. And we simply get that a sub z is minus mu naught I over 2 pi times the natural log of s. And therefore, my vector potential for the infinite line charge is simply minus mu naught I divided by 2 pi times the natural log of s. And you can check that the curl of A is indeed equal to mu naught I over 2 pi s times phi hat, just like you want. Did I miss my z hat? Oh, that's az. So yes, thank you. It is a, yeah, if it's a vector potential, we probably should write a vector. Thank you. So let's do that, yeah. So z hat is important. Thank you. But you see, if we are armed with the formulas in the cover of Griffiths, we can do this. It's not a big deal. This is not in Griffiths for some reason. Maybe it's in the homework, I guess. I probably just worked one of your homework problems. I'm sorry. You'll forgive me. Yeah, I mean, I know you guys have like the solution manual, right? I mean, I do. You know? I don't just assign you homework blindly. Like, I've looked at the solutions of all of those to try to make sure that they're not too horrible. I mean, this is the higher level physics course. There should be some genuinely horrible problems. If there's not, I'm not doing my job, you know? But not everyone should be horrible. What do you guys think? So the question is, what would this calculation look like if you tried to just integrate, if you tried to work this formula out for the infinite line? I mean, it probably can be done. But yeah. I mean, But this one you can see the directionality, right? Because this is what's this problem? We're talking about what? The infinite current in the z direction, right? And so the current goes that way, and guess what? The vector potential in the z direction. But it doesn't have to be that way, as you've seen from my example too, apparently. Because if we conjure up, trusting you guys, that if this is the, like that's the surface current, it's not just in the, like the surface current appears to be in the x hat direction, and yet this was in the y hat direction. It doesn't have to be, because it's filtering through the curl, and the curl can move things around. But anyway, I think it's like a startup guess. If I'm dealing with some problem trying to find the vector potential, if I was just to make like a guess, I'd guess like a vector field in the same direction as the current, maybe like an arbitrary one, and just try to work it out. Maybe that might be a decent strategy. I don't know. I'm just talking. I will say this. I think I need to look at something besides Griffiths for this particular stretch of the material. I think that there's something missing in Griffiths at the moment.